In this session, we are going to discuss about the medium access sublayer. Now, what is a medium access? The medium access is how these stations are accessing the media to send the packets or the frames from one station to another station or from one source device to destination device. See, basically, the medium can be a wired medium or wireless medium. What are the mediums? We have certain protocols which we follow when we access this uh, medium access. Now, in the first thing here is the channel allocation. In channel allocation, what is meant by channel allocation? See, basically, whenever you want to send a frames from one system to another system, so you need a channel through which you will pass on you will transmit the frames. So this can be allocated in two ways. One, static channel allocation, and the second one is dynamic channel allocation. In case of static channel allocation, the procedure is like this. They take the bandwidth and divide it with n equal sized portions. Suppose if I have n users, so we divide the bandwidth with n equal sized portions. So you will get a n slots, and each slot is allocated for each and every station. So within that time frame, within that slot, the stations can transmit the frames. So this is the process how it goes. But the major problem in this static channel allocation is if there are less number of stations, it works perfectly well. If there are more number of stations, then it becomes quite difficult. The thing is, there will be a lot of latency because until you complete the entire all the stations, you cannot give the control back to the first station. So this delay may not be suitable for many applications. And another problem here is once we allocate the time slots to the stations, and if some of the stations, if they don't use these time slots, they unnecessarily go idle. Means you are wasting the bandwidth. So this is another thing which causes some problem with this static channel allocation. And the second thing is dynamic channel allocation. Dynamic channel allocation, here the thing is you don't allocate any time slots for each and every station. See, the channel is open to all. Any station can access at any time. Okay, we have certain assumptions here, and there are five key assumptions in a dynamic channel allocation, and let us see what are the assumptions. First thing is station model. In this model, you have n independent stations, and each user generates separate frame for transmission. Once the station makes up the frame, it gets automatically locked until this frame is transmitted to the respective destination. And the second assumption is single channel assumption. Means you have a single channel available for communication for all the stations. And these all the stations mean I mean to say all they share the same channel. And but certain protocols, I mean certain softwares are there through which you can assign some priorities. That facility is also a part of this. But in common, this is the way how it is going to be happening. Then comes collision assumption. See, normally if two frames are transmitted simultaneously, there is a high chance that they may collide. Okay, if there is a sufficient time gap in between, they may not. But this problem, normally this collision happens when there are more number of stations are there, chance of collision is high. When there are less number of stations are there, chance of collision is less. But the collision may take at some place. And then comes continuous time and slotted time. In this fourth assumption, we have continuous time and slotted time. Continuous time means the continuous time there is no master clock divided time into discrete intervals. So the transmission can happen at any time. Any station can start transmission at any instant. But when it comes to slotted time, there will be a slots are there, and at the beginning of the slot only, the station should transmit the frame. So that means the difference between the continuous frame and slotted frame. And coming to fifth assumption, there are two things. One is carrier sense, and second thing is no carrier sense. In this case, carrier sense means normally if the carrier is busy, the station should not send any data. It should not pass on the packet onto the channel because if when the channel will be busy, if some transmission is going on, the channel will be busy. At that time, if a station tries to forward any packet, that leads to collision. So it only should send the packets when the channel is idle. And the B option is no carrier sense. No carrier sense means stations, they don't sense the channel, they simply pass on the packet. If they get the acknowledgement, everything is fine. If they don't get the acknowledgement within the stipulated time, gone. They have to retransmit the packet. So these are the two different parts of this fifth assumption. Now let's come to the multiple access protocols. Multiple access means many stations are accessing the common channel or common line. So in these, broadly we have three different categories. The first one is random access protocols. The second one is control access protocols, and the third one is channelization protocols. Now let us see this illustration. Here we have the random access and controlled access and channelization protocols. See, random access means any station can send data at any time at its will. There is no specific rule here. So normally in random access protocols, definitely there is a chance of collision. So the first one is Aloha, in which we have two different categories, pure Aloha and slot Aloha. And the second thing is CSMA, carrier sense multiple access. In this, we have three different strategies: one persistence, non-persistence, and probability persistence. And apart from that, you have another two more schemes like CSMA CD, CSMA CA. CD means collision detection, C means collision avoidance. Now coming to the second part, controlled access protocols. Controlled access means someone is controlling the entire access, someone is controlling the channel. So in this case, there will be no collision at all. It's totally collision free. In this, we have certain protocols like reservation, polling, and token passing. Of course, reservation means once you reserved it, and it never lead to any type of collision. Polling, the master starts poll one by one. So here also there will be no collisions. And token passing, whichever system has the token, it can transmit the packet. That's it. So the collision never ever occurs. And coming to the channelization protocols, FDMA, TDMA, CDMA, frequency division multiple access, time division multiple access, code division multiple access. These three ones are very popular in wireless technologies, and they are commonly used in GSM or in mobile phone communications. Now let us see these categories more in detail. So let us start with the first one, random access protocols. So as I said, Aloha. So Aloha is basically designed for radio broadcasting. In this method, stations share a common channel, and when two stations transfer simultaneously, a collision occurs and the frames are lost. So we have two different categories. One is pure and one is slotted Aloha. See, pure Aloha means the direct definition means at any station can send the frame at any time through the channel. So definitely this may lead to some sort of collision. So in the second one is slotted Aloha. In slotted Aloha, you can reduce these collisions because in slotted Aloha, you can see here. Let me show. Yes, in slotted Aloha, the frame starts only at the beginning of the time slot. So comparatively with pure Aloha, the collisions are less than in slotted Aloha. And you can see the here the how this works. The flow chart for this Aloha. You start the station starts sending K. K means attempt, first attempt. It sends the frame, and it takes around the waiting time is 2 into TP. TP means propagation time, means the time taken from a time taken by frame to travel from the source to destination. So since it should get the acknowledgement, so it is saying 2 into TP, so that one way data frame goes, the other way acknowledgement comes. That is 2 into TP. So if the station receives the acknowledgement, it's a success. If it doesn't receive the acknowledgement, it's a failure. Then it has to go for another attempt. Like that, it can go maximum to 15 attempts. So after going to another attempt, it waits for a certain moment of time, basing on R into TP or R into T time of T frame, and then it starts sending the frame. So this loop goes on till it gets success, but of course limited to 15 times maximum. So this is the about the flow chart, how it explains the flow of the transmission of Aloha. frames. So when you look into the vulnerability, the vulnerability time for pure aloha, we have a throughput pure aloha principle here. The throughput can be identified, can be found in pure aloha is given by s is equal to g into e to the power of minus 2g, whereas s is the throughput, and is equal to 0.184 in, and when g is taken as 1 by 2. In this case, we have an example here. So I'll use this. You can go to exam. It's quite simple. You just place these things in this principle, and the net magnitude throughput you will get it. That's it. So the second thing is, okay, slotted Aloha. We have already seen this, because in slotted Aloha the only difference is the frames are sent at the beginning of the time slot. And coming to vulnerability, this also have a different principle. LIS is equal to G into e to the power of minus g. In this case, it is e to the power of minus 2z, but in case of fraud LOH, it is minus g. The same way, you can take the same example and just implement the put all the values in that g and e and s, and you'll get the time. Okay, then let us look into the CSME. CSME is a modified version of Aloha, because in Aloha it never senses the channel. Okay, so the chances of collision is very high, of course, when there are more number of systems. Less number of systems, no problem. So in this CSMA, what it does, it first senses the carrier. Carrier sense multiple access means first sense the carrier. If it is busy, don't transmit the packet. If it is idle, transmit the packet. But still, because number of stations they are listening to the this transmission line, and they are sensing this carrier, and suddenly maybe sometimes what happen, 3 or 4 stations, the moment the channel is idle, they start sending, and that may lead to collision. So in CSM also collisions occur. So we have basically three strategies or three schemes in CSMA. One is one persistent, and the second one is P, probability, P persistence, and non-persistent CSMA. We'll see the diagrams which you can understand very easily. See, when you look into the one persistence, the station, it start sensing the carrier. So as far as it go on sensing, you can see continuously sense. It's a persistence. Persistently, it senses the carrier. The moment the carrier is idle, immediately it sends the frame. So that's why it's called as one persistent. And when you come to this probability persistent, see, the only difference here is the moment the line is idle, it sends the packet. But in P persistence, it also continuously persistently sends the carrier, and even the carrier it gets idle state, it won't send the packet. It waits for a probability, some probability of time. Of course, they have certain algorithms for this to identify this probability value. So basing on that, it waits for some time slot and then sends the packet. And the reason is, as I told you, if 3 or 4 systems they are observing the channel, the moment the channel is idle, if all the 4 systems that transfer the packet, that lead to collision. So instead of this here, since it's waiting for a certain amount of time, this will be, in some cases, this will be better than this. And the third thing is non-persistent. Non-persistent means non-continuous sensing. It first senses the carrier if it is busy. It doesn't continuously sense the carrier. If it thinks it is busy, if it finds it is busy, it goes off and comes after some time, and checks out. Busy, goes off, and it comes after some time, sends it. If it is idle, it sends the packet. If it is busy, goes back. So the only difference is there is no continuous here. There is no continuous. There is a non-persistent. And in these two cases, both are persistent because they are continuously monitoring the channel, whether it's busy or idle. So those are the one persistence, P persistence, and non-persistence, the three strategies or schemes in carrier sense multiple access.